Let's look at an example of applying the limit laws to evaluating a particular limit. Here we have a polynomial 3x squared plus 5x minus 7, and we are asked to evaluate the limit of this as x approaches 2. Previously, we saw, we explored ways to find limits by doing numerical computation, um, but that tends to be somewhat cumbersome. We can use graphs to visualize these things. That can be faster if you have something to do the graph for you. But both of those also have shortcomings in that they can sometimes lead us astray. A limit may appear to be approaching a particular value, but then either it does something very different at the last minute, or it turns out to be approaching a value that is slightly off from that. So in this section, we are beginning to develop methods of evaluating limits that are more rigorous and do not depend on those things. And our initial set of tools are the limit laws. The textbook lists 11 of these altogether, starts with 5 basic ones, and then from there goes on to several more. Our examples, the example I'm doing here and the examples in the textbook do reference back to those laws, and some of the exercises will expect you to work through those carefully as well. So I do recommend that you copy those laws all into one unified list in your notes so you can refer back to them. Do not try to memorize the numbers, unless you really enjoy memorizing things, but you're never going to be responsible for knowing, what's law number 7 or whatever. That's not what we're interested in here. But at the beginning, having that numbered list is very useful for reference as you start to learn what these laws are and how to use them. And over time, you should just internalize their meaning so that you can apply them without having to worry about them too much. But let's take this expression and start manipulating it with the limit laws. And I will cite these laws as I go. So first, we look at the expression we're dealing with and kind of look at the top level, the highest order operations here. We see that the structure of this, the highest level structure of this is that we have 3 terms that are being added and subtracted. And we have 2 limit laws that deal with addition and subtraction. Law number 1 tells us that if we're taking a limit of a sum, that we can turn that into the sum of the limits. So we have the limit as x approaches 2 of 3x squared plus the limit as x approaches 2 of the quantity 5x minus 7. As with many operations, there is a convention that this applies to just the next term. So if you have more than one term you're operating on, you need to include parentheses. That's important. The limit only includes whatever the next thing is. And this is by law 1. Now, we did this with our sum, but we see that our second limit is a difference. And law number 2 allows us to write the limit of a difference as a difference of limits. So the limit as x approaches 2 of 5x minus 7 is the limit of 5x minus the limit of 7. And you can apply more than one law at once if you are comfortable doing so. Just make sure that you are very clear on exactly which laws you are doing. Sometimes when I present this problem, I go straight to this step, and then off to the side, I just say by laws 1 and 2. But, it doesn't hurt to be a little bit more careful as we go here. Now here we have a couple of terms that have the similar characteristic of having a constant being multiplied by a variable expression. And law number 3 tells us how limits interact with a constant scaling like that. The limit of a constant times a function is that constant times the limit of the function. So we have here the limit of 3 times x squared. That means that we can basically pull the 3 out front of that limit and say that it is the limit of x squared. Similarly, in the second term, we have that constant 5. So we can say this. This last term I'll leave alone for now. We could simplify this, but I'd rather do those all in one go. This is by laws. Sorry, this is just one law. We did one law twice. That was law 3. Okay. Now, we look at what we have here, and examining each of these 3 limits in turn, we can see actually that those there's a law corresponding to each of those. Let's start with the simplest one. This last limit is the limit of the number 7. Now, if you look through your limit laws, you see that law 7, by coincidence, happens to be a limit of a constant. And the limit of a constant is just that constant itself. So I'll go ahead and just write 7 there. I'll come back and cite that in a moment. Hopefully this makes sense, right? This is a constant function. It is 7. No matter what value x takes on, this is always 7. So the limit will be 7, no matter what x is approaching. Backing up a little bit, we have a limit of x. And law number 8 tells us that the limit of x as x approaches a is a. That hopefully sounds a little bit circular when we say it. It should not be too difficult there. We're saying, okay, what does this function get close to as x approaches 2? But that function is x, so as x approaches 2, of course, x approaches 2. So that gives us 2. And then backing up here, we have this limit, and this is of the form x squared. We could apply the rule number 6 with the positive integer powers, and then subsequently apply this rule 8. But we have those kind of combined together in rule number 10, where the limit of an integer power of x is just whatever x is going to there. In this case, a is 2. So we have 2 squared. So this is by laws. Let's see what we used here. We used the constant law 7. We used the substitution of the variable in 8. And we used that power law in 10. So 7, 8, and 10 in the reverse order here are what we used. Now you see that we have basically evaluated all those limits. All that's left is to simplify the expression that we have, right? 2 squared is 4 times 3 is 12. 5 times 2 is 10, minus 7. So it looks like we get, what, a 15? Here we go. Doesn't quite fit on one screen here. But you see we have a chain of equality. We have this initial expression here, and I have a chain of equality where it equals this, and so on. And by our transitive property, we have evaluated that limit to 15. A couple things to note here. One of them is that, again, this lim that we write here is a kind of operator. It means that we're doing a mathematical operation on the expression that follows, and what we end up with should have some value. Notice that we keep these at every step until we evaluate those limits, right? The limit of 7 is 7. The limit of x as x approaches 2 is 2. The limit of x squared as x approaches 2 is 2 squared. When we evaluate them, we no longer write the limits, right? I did not write lim in this step because we have taken care of the limit. This is analogous to certain other operations. If you have something like let's say you have something like the square root of 3 squared plus 4 squared. You're doing a problem in geometry. Then you might do some steps of simplification and say, okay, well, 3 squared is 9, 4 squared is 16. 9 plus 16 is 25. You'll note that each step here I copy the square root symbol along because we weren't ready to deal with the square root yet. We were manipulating things. And then when we get to this point, now we can say, oh, and the square root of 25 is 5. Once we evaluate the square root, we no longer write the square root, right? So that's kind of what's going on here. We're doing manipulations. Sometimes we have more than one of these limits. So it might be, if you have a square root of 4x squared, and you want to manipulate that, you might break it up into two separate radicals, for instance, right? And then you can evaluate each of those separately. That sort of thing. And that's kind of what we're doing here, this limit operation. We're breaking it up in various ways and passing it through certain things and doing things like that. And then when we finally evaluate it, we have this here. Now, the astute among you might notice that the net effect of this was that we basically just sort of plugged 2 into this expression and got the 15. And this might seem like a lot of work to go through for that. And yes, there are circumstances under which we can perform that sort of direct substitution. And this is one of those circumstances. That's discussed more in the next subsection in the textbook. The direct substitution property. My next couple of videos will use that. But we will also see that we can't always use direct substitution. Sometimes that doesn't work. So we need to know something about how limits work and how to do other kinds of things with that. So at the beginning, when you're doing the first few examples of these things, your first few exercises, resist the temptation to just plug in the number and chug through. Take the opportunity to practice, working with these limit laws step by step and making sure you know how to manipulate the limits. Because, there will be plenty of occasions where we do need to manipulate limits on a more step-by-step level, and their evaluations can be a little bit trickier. But this is the basic idea for right now.